Welcome back, everyone, to what will be our final video on induction. We talked last time about how sometimes in order to make induction fit the particular problem that you're looking at, you might have to adjust what you consider to be the base case. So in the last video, for example, we did something where we wanted to start at 7 instead of starting at 1. In today's videos, we're actually going to change something different. In today's videos, I'm going to show you that sometimes you actually have to change the inductive step. And so the first example we're going to do is going to put together two things that we talked about in the last video. Namely, it's going to put together tilings and Fibonacci numbers. In this case, we're going to be talking about a grid that is 2 high and some amount wide. And let's take, for example, this grid, which we could tile, and we're tiling with dominoes again, so remember these are 2 by 1. So we could tile this, for example, like that. And here we actually want an exhaustive counting of how many ways there are to do this for this kind of board. So for a 1 by 1 board, that's the only way. For a 2 by 2 board, I could do it that way, that way. For a 3 by 3 board, let's see, I could do that, or I could do that, or I could do that. And so what I'm saying here is for a 2 by 1 board, I could do it in one way. For a 2 by 2 board, I could do it in 2 ways. And for a 2 by 3 board, I could do it in 3 ways. Of course, if I'd shown you this first, you might have guessed that for any given n, there would be n ways. But as soon as you got to n equals 4, already things would go awry because you would find out if you did this exhaustively for n equals 4, there's actually 5 different tilings that you can write down rather than 4. And that's because, as I suggest here, the number of ways to do this is actually the nth Fibonacci number, and it just so happens that the Fibonacci numbers start out 1, 2, 3. Now, I'll also go ahead and note that in the last video, I had a somewhat extended digression about indexing the Fibonacci numbers and how you might start at 0 or 1 with counting and all of these sorts of things. And I did that because in anticipation of this example, I expressly wanted to index the Fibonacci numbers this way. Why did I want to choose this indexing? Well, because this is the indexing that makes the thing we're trying to prove actually true. Otherwise, we run into problems. So already, just in 2 examples of dealing with the Fibonacci numbers, 2 different indexings have been the natural choice. So I just really wanted to warn you that you're going to see all kinds of indexings of your favorite sequences, and it's just best if you just roll with it when it shows up. So let's figure out what happens when I try and write this up by induction. Okay, so I'm going to start here with scratch work. Now, the scratch work certainly includes whatever base case I want to take. If I want to take 1, 2, 3, whatever of those I happen to want as a base case, we're good. Where things are going to get interesting is when I try and figure out what's going on with the inductive step. So if we were to write our traditional inductive step, it would say that what we're trying to prove is that if a 2 by k board can be tiled in fk ways, then a 2 by k plus 1 board can be tiled in f sub k plus 1 ways. So in order to start visualizing this, I'm going to visualize what it is I'm going to have to prove. I'm going to have to prove something about a 2 by k plus 1 board. So let me start by just drawing a 2 by k plus 1 board. Now, we know from our previous experience with induction that we're going to need to use this piece we've assumed. That is, we're going to have to use the inductive hypothesis, which is something about how many ways a 2 by k board can be tiled. So in particular, I'm going to have to find a 2 by k board. And that's not so difficult. Namely, that's a k, if this whole thing is k plus 1. And so I know how many ways there are to tile this piece. Now, how does that help? How does the fact that I know the number of ways to tile this piece that I've blocked off in black help? Well, that also tells me the number of ways to tile a k plus 1 board if I make one agreement, which is that I have to put a domino here. right? If I tile the k by 2 board like this, then in order to fill up my k plus 1 board, I would need to put a vertical domino. So summarizing that observation, the number of ways to tile a 2 by k plus 1 board with the rightmost domino vertical is the same as the number of ways to tile a 2 by k board with no restriction. So far, I like where we are because we've related talking about tilings of 2 by k plus 1 boards back to tilings of 2 by k boards, which is exactly the kind of thing we want to do when we're writing down an induction proof. Relate the bigger case back to the smaller case. Now this is getting very, very cumbersome to write, so I'm going to introduce some notation, and I'll decide later whether I actually want to retain that notation in the proof or if I want to omit it when I'm actually writing up the final proof. But for scratch work, I want to be doing as little writing the same things over and over again as possible. So I'm going to go ahead and just denote by big T sub k the number of tilings of a k by 2 rectangle with no restriction. Likewise, I'll write a sub k for the number of tilings of a 2 by k rectangle with the rightmost tile vertical. The advantage of this notation is that I can now super cleanly summarize this observation as saying that a sub k plus 1 is equal to t sub k. Again, all this equation says, once we've written down this notation, is that the number of ways to tile a 2 by k plus 1 rectangle with the rightmost tile vertical is equal to the same as the number of ways to tile the k by 2 rectangle with no restriction, which is just embedded into these symbols big T sub k and big A sub k. There is one problem, though, which is that I haven't counted all the domino tilings. I've only counted the domino tilings where the last domino is vertical. Indeed, the fact that this comes up so naturally suggests I probably also need to consider the case where the last domino is horizontal. I'm going to draw a picture just so we can visualize that. Okay, so this is k plus 1 again. And now when I'm counting these, I'm really tiling this piece that remains. But how big is this piece that remains now? This piece that remains is now k minus 1, because it's k plus 1 minus 2. I'm going to go ahead and give this a name 2. Namely, I'm going to say that b sub k is the number of ways to tile a 2 by k rectangle with the rightmost tile horizontal. And I can again summarize my observation here in a pretty straightforward way, which is that b sub k plus 1 is the same thing as t sub k minus 1. Now I want to note this proof work, or whatever you want to call this thing we're doing so far, has gone in some kind of unexpected directions. There was no reason when we set out to this question to think it was going to have anything to do with whether things were vertical or horizontal, but when we tried to find our 2 by k board and our 2 by k plus 1 board because we wrote down what we thought the inductive hypothesis was going to be, we sort of naturally fell into considering tilings where the domino on the right-hand side was vertical, which led us to define this a sub k. But once you've defined this a sub k, you're basically forced into defining this b sub k. Because if I'm going to think about places where this last tile is vertical, I might as well also think about places where it's horizontal. So let me summarize what we have so far. So the very first thing we realized that sort of got the whole ball rolling on this train of thought was that a sub k plus 1, the number of ways to tile a 2 by k plus 1 board with the rightmost tile vertical, was exactly the same thing as t sub k. Then, when we thought about the other thing, so instead of thinking about a vertical rightmost tile, when we think about a horizontal rightmost tile, that turned out to be the same as the number of tilings of a 2 by k minus 1 board by dominoes. Lastly, I want to make a new observation that puts these things together, which is that the thing we really care about is t sub k plus 1, which is to say the thing we really care about is the number of ways to tile a 2 by k plus 1 board. But because there's really only two ways to put a domino onto a board, namely horizontal or vertical, the rightmost domino has to either be horizontal or vertical. So this t sub k plus 1 is actually a sub k plus 1 plus b sub k plus 1. But, and here's where things start getting put together nicely, because of the two previous facts, if I put them together with this new observation, we get that t sub k plus 1 is the same thing as t sub k plus t sub k minus 1. And now we're in a place where things look very Fibonacci-y. So, let's rewind all the way back to what our first guess at the inductive step was. Namely, our first guess at the inductive step was that if k is a positive integer and a 2 by k board can be tiled in fk ways, then a 2 by k plus 1 board can be tiled in f sub k plus 1 ways. So everything written here we've proven. Nothing here involves our induction. But what our inductive hypothesis as it's currently written actually says is that t sub k is the same thing as f sub k. So in other words, it says t sub k plus 1 is f sub k plus t sub k minus 1. And what we want to prove is that this t sub k plus 1 is equal to f sub k plus 1. And if you're following all of this, you can probably see what we'd need. Namely, I really want to know that this is f sub k minus 1. Why do I want to know that? Because if I did know that this was f sub k minus 1, then I would have t sub k plus 1 is the sum of the kth Fibonacci number and the k minus first Fibonacci number. But by definition, the sum of the kth Fibonacci number and the k minus first Fibonacci number is the k plus first Fibonacci number. So that would exactly say that t sub k plus 1 was f sub k plus 1, and then we would be done. That fantasy world sounds great. However, I don't get into that fantasy world with this inductive step. In order to get into this fantasy world, I actually need my inductive hypothesis to say something not just about the previous case, which is what our inductive hypothesis has always said before. I actually need my inductive hypothesis to say something about the previous two cases. There's one more annoying piece here that you'll come to if you stare closely at all of this. And that piece is, what case is this circle of ideas actually true for? Is it true for all positive integers k? Well, there's potentially a slight problem if k is 1. Namely, if k is 1, this ends up referring to t0, and then this ends up referring to t0, which is something about the number of ways to tile a 2 by 0 chessboard with dominoes. And I don't really want to get into how we should exactly interpret that. It turns out if you really had to interpret it, it's 1, but I'd just rather not. And so I'd rather just think of everything we just said as being true for k in z greater than or equal to 2. Once k is at least 2, then these k minus 1s become 1s, and everything works out the way we want. But, and here's the one more wrinkle I mentioned, the fact that this only works for k starting at 2 means that I actually don't get to start applying the induction until I'm looking at a k plus 1, which is equal to 3. And what that means is that I'm going to need two base cases. Namely, I'm going to need to handle n equals 1 and n equals 2 as base cases, and then proceed from there. So that scratch work now includes all the pieces that we have to put together in order to write down this proof. But now let's actually write down the proof. So remember, the thing we're trying to prove is that every 2 by k chessboard can be tiled in f sub k ways, where f sub k is the kth Fibonacci number. And so before we even get anywhere near the induction piece, we're going to start by introducing the notation that we came up with in our Scratch work. Now, remember, we know we're going to need all of these pieces. So let's go ahead and get these out of the way to start with. And so again, we're going to write down a lemma here, which is just saying, hey, I'm going to write down all of these pieces that I'm going to need in the proof just separately so that when I get to the point in the induction when I need them, I can just refer back here to the lemma. So of course I have to have a proof of the lemma, but fortunately each of these pieces in the lemma is fairly short. Again, the first piece here is just saying, well, there's only two kinds of ways to put a domino, horizontal and vertical. So that rightmost domino, it's either horizontal or it's vertical. So it's either counted by A sub k if it's vertical or B sub k if it's horizontal. So I think a picture like this is helpful. And then you can follow up the picture with something like, once a vertical tile is placed at the right, a 2x board remains to be tiled. And that's really just by definition saying that if I go to tile a 2x+1 board, and I put a vertical tile at the right, then the number of ways to do that is exactly the same number of ways to tile a 2x board. So what about a 2x+1 board where I put horizontal dominoes at the right? Well, and so once I place these two dominoes here horizontally, then I have a 2x-1 board left to tile. And so that proves every piece of the lemma. And so now we're ready to get back to the proof of the main result. So we can put our proof box there for the lemma and say we return to the main proof and proceed by induction. Remember that in this instance, we have two base cases, which were n equals 1, where there is one tiling. And so here we're checking that T1 equals F1. And then for n equals 2, there's two tilings, and we're checking that T2 equals F2. And now for our inductive step, we're going to assume that if k is in z sub greater than or equal to 2, and t sub k equals f sub k, and t sub k minus 1 equals f sub k minus 1, then t sub k plus 1 equals f sub k plus 1. This is now what we have to prove. And note, because of my Scratch work, I knew that I wasn't going to get by with only assuming the previous case. I wasn't going to get by with only assuming t sub k equaled f sub k. I was going to need to know both that t sub k was f sub k and that t k minus 1 was f sub k minus 1. And now we've really buried most of our work for this in the lemma. What were the three pieces of our lemma? Well, we rigged it up so the three pieces of our lemma were the statement that t sub k is a sub k plus b sub k, that a sub k plus 1 was t sub k, and that b sub k plus 1 was t sub k minus 1. Now, we finally get to put to use this whole bit about the Fibonacci numbers, which you might notice, despite the fact that this is a proof about the Fibonacci numbers, we've not really talked about the Fibonacci numbers in this proof basically at all. But our inductive hypothesis is exactly that t sub k is f sub k and t sub k minus 1 is f sub k minus 1. So thus, using that inductive hypothesis, we get that t sub k plus 1 is f sub k plus f sub k minus 1. But f sub k plus f sub k minus 1, that's just f sub k plus 1 by the definition of the Fibonacci numbers. And thus, we finally have gotten to t sub k plus 1 is equal to f sub k plus 1, and so that means we're done with the proof. So this whole time I've been using this analogy of a frog hopping across lily pads for induction. And I've said things like, okay, well, you start at the n equals 1 lily pad, and you prove that that one's good by checking the base case. And then you prove that once you're on a lily pad, you can always jump to the next lily pad. And so in our typical induction problems, as in the previous videos, we've gone, okay, start at the n equals 1 lily pad, and then show, okay, I can go from any lily pad to the next one. What we've done here is actually a bit more complicated. Our inductive step here is basically, in terms of lily pads, if two consecutive lily pads are safe, then so is the next one. But if you look closely at this, it makes sense that one base case isn't enough. If we'd only done one base case, we wouldn't have had 2 consecutive lily pads to start with, and we couldn't have gotten the ball rolling. But once we consent to having a second base case, then we can apply our inductive step, which says, okay, once you've got 2 consecutive ones, the next one's fine. So these 2 are consecutive. So then the next one's fine. But now these 2 are consecutive, so the next one's fine. These 2 are consecutive, so the next one's fine, and so on forever. And this works exactly like our regular old-fashioned induction. It's just that we needed to make our inductive step slightly more complicated, and in the process of making our inductive step slightly more complicated, we also had to change how we presented our base cases. As a result, make sure you always carefully state what your base cases and inductive step are. You can't just assume that the reader knows what inductive step you're talking about, because in some examples you'll want to change it. So here's another example where we get to do something similar to the previous example. Here we're going to prove that if I take an integer greater than 40, then it's possible to write it as a sum of 5s and 11s. So just for example, I could write 40 itself as 5 plus 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 5. The origin of this question, by the way, people usually frame this in terms of making postage with 5 and 11-cent stamps. However, stamps aren't really worth cents much anymore, so I just went ahead and just said we're just adding these numbers together. Likewise, if I wanted 41, I could take an 11 and then 6 5s. Or if I wanted 42, I could take 2 11s, and then 4 5s. Or 43, 3 11s and 2 5s, or 44, 4 11s. Note there are plenty of numbers that you can't write in this way, they just happen to all be smaller than 40. So for example, if you try writing 12 as a sum of 5s and 11s, you're not going to succeed. And there are a variety of numbers less than 40 for which this is not possible. But once you get to 40, somehow magically, it always stays possible. Now, if you start thinking of this as an induction problem, then you're starting to think, okay, how do I get from step 40 to step 41? What am I doing as I go down one step? How do I go from here to here, or here to here, or here to here? And if you look at this amount of data, just what I've shown you, you might guess, okay, well, every time you want to go up by 1, you take away 2 5s and replace it with an 11. Math checks out. Minus 2 5s plus 11, that would be plus 1. That's great, except when you get to this spot where you're back to 44, you can't actually take away 2 5s because there aren't 2 5s left. And so when you get back to 45, you actually need 9 5s. And so if you try and write this as a standard induction question, where you're always going from one thing to the next, to the next, to the next, it's going to result in a really messy proof by cases when you go to write down your inductive step. But let me make an observation, which is that if instead of trying to leap ahead by 1, I leapt ahead by 5, I think that's a pretty easy proof to write. So what I'm saying is, if I let my inductive step be that if k is an integer 40 or greater, and it's a sum of 5s and 11s, then so is k plus 5, well, this is so easy to prove, I'm not even sure what to write, because, well, if this number is a sum of 5s and 11s, well, I just threw in a 5, so of course this number is now a sum of 5s and 11s. But if I go back to my lily pads, and think about what that means in terms of base cases, well, if I just wrote down one base case, this isn't going to be anywhere near enough. Because one base case will get me from 40 to 45, from 45 to 50, from 50 to 55, and so on, but I'm missing tons of numbers in between. So actually, in fact, how many base cases do I need? And we actually need 5. And that's because if I now go from 41 to 46, and then onward, 42 goes to 47, 43 goes to 48, 44 goes to 49, and these all keep bouncing along happily on their merry way onward through all the numbers. And this will hit every integer hereafter, and the reason for that has to do with the division algorithm, right? Remember, the division algorithm says that if you divide by 5, every number is either a multiple of 5, 1 more than a multiple of 5, 2 more than a multiple of 5, 3 more than a multiple of 5, or 4 more than a multiple of 5. And so once I throw in 40 into my list of base cases, then that gives me every multiple of 5 from 40 onward. Likewise, 41 is 1 more than a multiple of 5, so that gives me every number that's 1 more than a multiple of 5 from 41 on forward, and so on. And so each of these 5 base cases happens to take care of one of our division algorithm buckets. And so as a result, basically what I've written here is almost a complete proof. These are the base cases. That's the inductive step. The inductive step proves itself, and then I have to include language about the division algorithm to say that the combination of the division algorithm and the inductive step covers everything. And then I'm done. The last example I want to talk about in this video is the fundamental theorem of arithmetic. Now, this is something you've probably seen before, but probably never really thought about why it's true. But it's the thing that tells you that you can write down every positive integer as a product of primes, and in fact you can do that in exactly one way, as long as you count correctly. Incidentally, while we're here, this is why 1 isn't prime. What do I mean? Well, if 1 was prime, and I then went to write down, say, 21 as a product of primes, I could write it as 3 times 7, or I could write it as 3 times 7 times 1, or 3 times 7 times 1 times 1, and the list goes on, and these aren't the same. We already have to sort of accept when we say a unique way that we don't consider 7 times 3 to be different than 3 times 7. And that's fine, that's just changing the order. But throwing in an arbitrary number of 1s certainly would ruin this uniqueness piece. Now, I'm not going to prove for you the uniqueness part. That turns out to be a little trickier. But I am going to prove for you the existence part. Namely, I'm going to prove to you that every positive integer can be written as a product of primes. And the proof here is really clever. So let me show this to you. So my base case here is just going to be n equals 2. I don't have to check anything more than that. And the cleverness in this proof is entirely baked into the inductive step. And the inductive step here is to say, not just if k can be written as a product of primes, not just to say if k and k minus 1 can be written as a product of primes, but to say that if in fact every number from 2 up to k can be written as a product of primes, then you can write k plus 1 in that way as well. And so here is the proof. We're going to suppose the inductive hypothesis part. That is, we're going to suppose that every integer from 2 to k can be written as a product of primes. And then we're going to consider k plus 1. And I claim now there's 2 cases. This k plus 1, either it's prime or it's composite. Remember, we have that one annoying number that's neither prime nor composite, but that number's 1, and our k here is already starting at 2, so k plus 1 is never going to be 1. So we only have to think about primes and composites as soon as we get above 1. Well, if k plus 1 is itself prime, well, then it's a product of primes, just as 7 is a product of primes, because it is the product of the primes 7. Likewise, if k plus 1 is already prime, then we're done. On the other hand, maybe k plus 1 is composite. If that's true, then there exist a and b that live between 1 and k that multiply together to be k plus 1. Note my notation here. When you shove an a comma b in the middle of an inequality like this, what I'm saying is that a and b are both between 1 and k plus 1. And this is just literally the definition of composite. But, and here's the magic of where our inductive hypothesis comes in, a and b are less than k plus 1, and bigger than 1, and so a and b are exactly the kind of numbers that we assumed can be written as a product of primes, namely they're numbers between 2 and k. But, well then, a times b is product of primes 1, whatever way a can be written as a product of primes, times, and then whatever way b can be written as a product of primes. But the product of two products of primes is a product of primes. So what does this say back in terms of our lily pads? What's really happening here? Well, we write out our lily pads, and we're starting at 2, because that was just where this particular statement had started, and so on. And what our inductive step here really said is, if every lily pad up to the kth is safe, then so is the next one. So here, we started with our base case of just 2, and then we noticed, well, hey, every lily pad up to the second one is safe, so the third one is 2. Hey, every lily pad up to the third is safe, so the fourth one is 2. And so on in this cascade, and this cascade is very similar to the cascade that we got for our regular induction. Now, I'll note people often call this strong induction. I don't think this is a particularly helpful thing to name, but people will sometimes use that name. So if you hear someone say this proof is by strong induction, what they're telling you is that they want to do an induction where their inductive step is assuming that every previous one worked. But as you've seen in this video, hopefully, there are a bunch of different ways you can combine an inductive step and some base cases to prove a result. All right. In the next video, I'm going to talk about some classic proofs and a classic proof method called proof by contradiction, which will show up in a couple different proofs that are famous enough that I feel like I'm obligated to show them to you. And then we're going to sort of wrap up our main talk about proof methods for the quarter. Now, we're still going to be proving things for the rest of the quarter, so don't get too excited. But as far as the how to prove stuff, this end of third week is basically going to wrap up our main discussion on new ways to prove things. But that's all for now. I'll see you next time.